Let's just wait 2-3 minutes after the time. Okay, let me start. So this is the week 5 problem solving session for advanced physics. Okay, so just like the previous other classes, we will start with the assignment, discussing the assignment questions. And so first we will look at the assignment question of week 4, and then we'll develop some concepts. We'll revise and try to derive certain things because this advanced atmospheric physics, there is so much of mathematics here. So we will try to derive and understand the things, and so that we can solve this week 5 assignment questions. Okay, so this is the proper plan for today, and fine. Let me I can switch off video right now. Just a minute. Yes. Open the assignment. Yeah. So this is the fourth week assignment questions. Okay. So so the first question of the week 4 assignment asks that which of the following force is important in both small whirlpool and the tornado kind of atmospheric dynamics. So one thing we must be very, very careful about, that whenever you have some kind of a whirlpool or tornado or cyclone even, these are all cyclonic circulations. Okay. Now the thing, the difference between a small whirlpool, tornado, and a cyclone depends upon the spatial scale. So we have discussed about the spatial scale in the last couple of problem solving sessions. So the only difference between the whirlpool or a small scale system and a large scale system is the spatial scale. Okay, a small whirlpool happens in a very shorter or a smaller region. Similarly, a tornado compared to a cyclone, a tropical cyclone, or you can call it as a hurricane. Okay? So it is the scale which matters. But in all of these systems, ultimately what happens is that you find some kind of a, so in all of the system, whether it is whirlpool or whether it is tornado or whether it is a cyclone, a large system, you will find that there is always a low pressure center. Okay, there is always a low pressure system at center, and as you go away from it, the pressure increases. Some high pressure compared to this. Okay, some high pressure regions will exist. So the only force which can exist in whirlpool, tornado, as well as cyclone, river, is the pressure gradient force. Right? Because based on that, the wind motion will be generated. Right? So, therefore, the force which exists in all three is the pressure gradient force. Pressure gradient force. Okay. Pressure gradient force. Now, so we have derived this pressure gradient force at the very beginning. So now let us go to the question again. Force is important in both small whirlpool and a tornado. Tornado is much larger in scale compared to a small eddy or a whirlpool. Okay, but look at the other things, the other options. Okay, first is the Coriolis force. See, this Coriolis force will only act when the spatial scale is very large. Why? Because if you remember, let us talk about the horizontal Coriolis force. If you remember, it depends on the planetary this rotation speed, 2 omega sine phi. Right? This is what we have done. This is the F. And we have seen that the horizontal Coriolis force is F into V, some velocity. Right? This is what we have seen. So, this is depending on the planet's rotation. Okay. So, if the movement, or if I would say the spatial scale, okay, if the spatial scale is very small, okay, if it is small, then these things will not act. Coriolis, centrifugal is itself very small, so centrifugal will not act. So these forces, Coriolis force or centrifugal force, will be, I mean, it will be acting, but it will be very, very little. Its contribution will be very, very little. And again, gravity. See, all these systems, these are mostly a big horizontal systems. So vertical has a very little effect compared to the horizontal. Look at the extent of the cyclone. It is much more stronger in the horizontal scale, about 1,000 kilometers, about 500 to 1,000 kilometers. I mean, when you see a cyclone over Bay of Bengal, you'll see that the entire Bay of Bengal is covered. So gravity is still acting. It's not that gravity is not there, but the effect is much stronger for the horizontal scale forces. Okay, so these forces will act, but contribution is very small. Okay, so this is the concept for this. Okay, while the other options are not right because their contribution is very small because we are talking about very small scale phenomena. All right, fine. Next question is, in which kind of motion Coriolis term is negligible? So, as you can see here, both A and B are the correct options. Why? Because the A option, what is it saying? Motion in horizontal direction of a small whirlpool. We have just now discussed. Small whirlpool, it's just like an eddy. Like, for example, you have some leaf, right? A leaf is rotating in a normal day. Okay, so you can see that the leaf rotates in a very small region. Okay, so that is a kind of a small whirlpool or a eddy kind of a structure, which is a very small scale. Their Coriolis force has nothing to do because in one case you have Earth's rotation being involved, and in the other case it's a very small scale eddy. So it will not be. Uh, I mean, the Coriolis force's contribution will be very very small. Similarly, again, those two which has a small whirlpool related thing is having Coriolis force negligible. Next is motion in low pressure systems. Again, low pressure systems means as good as cyclones, I would say. Okay. But there is a distinction between a low pressure system, a depression, and a cyclone, particularly based on the velocity, the wind speed. Based on the wind speed and the intensity of convection, you generally categorize it as a low pressure system or a depression or a cyclonic system. But even if you are considering a low pressure system, it's a very large scale process. So for the large scale process, Coriolis force will act, but for small scale processes, it is negligible. It acts, but it is very small as compared to the pressure gradient forces. Okay, so the first and second are quite related. Third is in which kind of motion gravity is important. Anything which is related to vertical motion, that should be one of the cases. So, motion in the vertical direction of a tornado. Yes, when you have specified vertical direction of tornado, there the gravity is important, definitely. But if you are comparing the horizontal extent and the vertical extent, then the horizontal extent is much stronger compared to the vertical extent. Okay, so vertical direction, wherever you have vertical direction, there the gravity is absolutely important. And the third option is motion in horizontal direction of tornado. There, gravity is not important. Gravity is acting only in the vertical component. Horizontal components does not have any influence on the vertical component. They are actually perpendicular or orthogonal to each other. So, just similar to a case like in physics, when we used to do this vector kind of a problems, we what we do, we have our x coordinate, we have our y axis. So the forces which are acting in the x axis has nothing to do with the forces acting in the y axis. That is what we generally take, right? Because they are perpendicular to each other, orthogonal to each other. So the component of forces at j cap direction has nothing to do with the I hat direction most of the times. Okay, so that is what we are doing here. So both A and B are the correct option. Why? Because it involves the vertical direction. Okay. Next, I can see there are a couple of questions which are related to waves. Although they are, I think, informed in the fourth week lecture, but I think many of the properties of these waves is not been introduced. But suddenly, why these questions are there, I'm not very sure. But still, we should know a couple of things based on our basic atmospheric physics. Okay. Fourth question deals with which of the following waves has the largest wavelength. There are many waves here. So here, Rossby waves is the correct option. Uh, I can't tell you why, because there are, I mean, mathematically, I cannot prove you right now why the Rossby waves has higher wavelength, but with in terms of atmospheric dynamics, I can tell you that why Rossby waves has the largest wavelength as compared to any other waves. We will discuss these waves, not the Kelvin waves for sure, but acoustic waves and internal gravity waves. Those things we will be discussing. Okay, so I will come to it. I will show you some things and it will be clear. Let's skip for the time being the question number 4. Let's go to question number 5. Which of the following waves are most likely to exchange energy with each other? So what happens is that exchanging energy happens in nonlinear waves. Linear waves generally tend to have nothing like this wave exchanging of energy. But in general, the surface gravity waves, they have a tendency to exchange energy with the other waves or with the atmosphere like that way. Okay. So waves in solids and general sound waves, they can also be nonlinear, but this surface gravity waves is a particular wave, particularly in the atmosphere, where you can see that waves can interact with each other. That's the thing. Okay. Sixth thing, a small Rossby number of a system indicates that. Now, this is a good question. Small Rossby number of a system indicates. So, we have done scale analysis of horizontal momentum equation, and there we have shown a Rossby number, and we have discussed in the last problem solving session also. So a smaller Rossby number results in a geostrophic kind of a balance, right? Where which are the forces which are important? The pressure gradient force and the Coriolis force. Geostrophic wind is formed due to the balance of pressure gradient force and Coriolis force. Therefore, it is strongly affected by Coriolis force. A option is correct. It is strongly affected by pressure forces. C option is correct. So both A and C are the correct options. Seventh question is that cyclogeostrophic balance. Okay. So what is a cyclogeostrophic balance? See, I have already mentioned in the last problem solving session that you have a cyclotropic balance. Okay, you have a cyclotropic balance. What is that? Cyclotropic balance is the balance between the pressure gradient force and the centrifugal force, right? And it is also a geostrophic balance, which we were discussing. Geostrophic balance is what? It is a balance in equilibrium of, or it is an equilibrium between pressure gradient force and Coriolis force. Now add on these two things. Cyclostrophic plus geostrophic gives you cyclogeostrophic. It is as good as sorry, cyclogeostrophic balance. So it is as good as your gradient wind balance. Okay. Why? Because it consists of both the balance of pressure gradient and centrifugal and pressure gradient and Coriolis force. So all these three forces should be involved in the cyclogeostrophic balance. This one. Okay. So if you come back to the question, so see, all these three are the correct options. Okay. So this is the cyclogeostrophic balance. Okay. And the last is acceleration following the relative motion in a rotating frame equals the sum of. Okay. Acceleration following the relative motion in the rotating frame. Okay. So question is in any. So this is the eighth part. This is the seventh part. Sixth question, we have the Rossby number. So whenever Rossby number is less 10 to 0, winds become geostrophic. Okay, winds become geostrophic. And geostrophic winds has pressure gradient force and Coriolis force. This is the sixth question. Okay, fifth question is the surface gravity waves. Although this is a kind of confusing thing. Okay, other waves which are mentioned there also you can find some exchange of energy between the waves because they can be non-linear sometimes. But major, okay, in the atmospheric sense, maybe this is one of the correct options. And for the first and second, we have the scale, which is being important, and in fact, the third and fourth also, where the gravity and all those things are discussed. Eighth question, it is saying that in rotating frame for the relative motion, which forces are important. So in a rotating frame, which is a non-inertial frame, we know that all real forces will exist in a rotating frame, plus the pseudo forces will exist. Right? In rotating frame, in a non-inertial frame, all real forces plus all pseudo forces must exist. But in an inertial frame of reference, where there is no acceleration of the frame, non-accelerating frame of reference, there only real forces will exist, no pseudo forces. But since it is being asked that in a rotating frame, that is in a non-inertial frame, which forces are important, and in atmosphere we know that which are the real forces, which are the pseudo forces. So real forces, as given in the question, let us see, pressure gradient force. It is a real force. Gravity is also a real force. And effective gravity means what? Gravity plus centrifugal. Frictional force is also a real force. So that will also come plus the pseudo forces, Coriolis force and centrifugal force. That will also come. So all of the above will be the correct option here. Okay. So for the relative motion in a rotating frame, both real forces as well as pseudo forces will act. But if it is relative motion in a non-rotating frame, if the arc is stationary, then what will happen? Only pressure gradient force, friction, and gravity will act. Effective gravity will also not be acting. Okay, because effective gravity consists of centrifugal force. Just keep in mind. Okay, so we have already done most of the things except for question number 4, the Rossby waves. So I want to again draw your attention towards that this website, Windy, which I have shown lot many times because it's a good visual. Okay, so I have shown you in the last time about the jets, right? So okay, so these strong winds are the jets. Sorry, let me just. Okay, so this is at a height of 5,500 meters. Okay, let me go more to the downward direction whether I can go or not. I'm not sure. Let me open another tab. Okay, so let's see this. Here. I'm going into the southern hemisphere. Okay, where you will be seeing these strong jets. Okay, so entire world, if you see further to the south, I think it is too much. Yeah. So what I have shown in the last, see this strong wind region which is shaded like violet or some darker shades. Look at this. This has a very nice or a strong wavelength. Okay, and it is actually covering the entire globe. I have shown only the, I'm seeing here only the south of African region and south of the Australian continent. But look at this, these strong winds or strong wind region is actually circumferring the entire globe. And how it goes, this is how. So about the pole, if you have an earth like this and somewhere it's okay, and what happens is that at the mid-latitude region, suppose this is the mid-latitude region, you find stronger and larger wavelengths. Okay, this is the kind of a pattern which the winds are called. So winds goes like this. Okay, so let me. So this can be zoomed out like this. Okay, so something like this, but this is the low atmospheric low, and this is high. Okay, and the winds generally tend to flow like this, which I have shown just now in the windy. Okay, so this is how the things goes. This jet streams, which I have shown, or this large scale pattern of waves, is generally sometimes called as the Rossby waves. Okay, but these are the mid latitude Rossby waves. There are Rossby waves which exist at the equator also, but I am talking about mid latitude Rossby waves. Okay, these are mid-latitude waves. This is a strong wave-like structure which circumferes the entire Earth, and its wavelength is very very strong, as you can see from the planetary figure which I have shown in the video. Okay, so just remember right now for the time being that Rossby waves generally has a larger wavelength compared to any other waves like Kelvin or acoustic waves or other internal gravity waves kind of thing. Okay, we will see much more when we derive these Rossby waves and all. Okay, so with this, I think the assignment part is over. Now we can move to some week 5 things. Okay, so just give a moment. In the last problem solving session, we were discussing about the perturbation method. And what we have seen so far in the perturbation method is that we have listed down that that your perturbation, say u dash, suppose, must be always less than, much less than the base state. This is the base state. Base state means you can say that time mean or special mean state. Okay. So this mean can be, the averaging can be done in x, y, or t. Generally, we do it like this. Okay, this is one of the things. So it's all based on some assumptions. Second is that both u dash and u bar must follow the dynamic equation. Okay, must follow the dynamic equation. Okay, or should satisfy the equation. Third is that product of the perturbation. So suppose u dash is one of the perturbation variable, v is another variable whose perturbation term is v dash. This term is zero. Okay, negligible. Okay, so these are the couple of things for the perturbation theory, and we were trying to apply it in your horizontal momentum equation, and we have discussed that suppose u is the zonal velocity and we are writing this as x, y, z, t, which is equal to u bar, which is also a function of x, y, z, and it is suppose mean in time. Okay, only the time everything is done. We will further assume later on. Plus u dash, perturbation will be in everywhere, so both in space and time. Similarly, v meridional wind x, y, z, t, which is equal to v bar x, y, z for the time being plus v dash x, y, z, t. Similarly, you have w and whichever variable you have, you can put it like this because in the horizontal momentum equation, all these things are required. So I am writing it. So I will show you that how the perturbation technique works and then apply it to derive some wave dynamics. Then P, the pressure, x, y, z, t is equal to P bar, which is a function of x, y, z for time being, and P dash, which is x, y, z, and t. Similarly, finally, you have density rho x, y. In the pressure gradient, we have density, right? So z t is equal to rho bar x, y, z plus rho dash x, y, z, and t. Okay, these are just couple of, this is how we write the perturbation terms. Now, based on this, let us write the horizontal momentum equation. So, what is the horizontal momentum equation? Full, complete. So, this is the partial delta u delta t, u delta u delta x plus v delta u delta y plus w delta u delta z, okay, is equal to minus 1 by rho delta p delta x. And let's write the queries if v. Fine. This is the x direction, zonal momentum equation, where u is the zonal velocity, v is the meridional velocity, w is the vertical velocity, rho is the density, p is the pressure, f is the Coriolis term, and v is the again meridional velocity. This is the x momentum equation. Perfect. Now what we will do is that we will put all these things, these things in this particular equation. Let's do that and try to solve further. Okay, so delta u. So delta t of what we will write is u bar plus u dash. Fine. Next, u bar plus u dash delta x of u bar plus u dash plus v bar plus v dash delta y of u bar plus u dash. Perfect. Plus w bar plus w dash delta z of u bar plus u dash. Then on the right hand side, minus 1 upon rho bar plus rho dash delta x of p bar plus p dash. All right. And finally, you have plus f, it does not have, it's a constant, into v bar plus v dash. That's all. This is the perturbation method we have applied here. Perfect. Let's go further and see. Based on the perturbation technique, what we can derive? See, U bar is already time average. So we will delta t of U bar, because it's a time average, it's a function of x, y, z only. So this can be removed, this can be 0. So what I get is delta U dash by delta t plus. Okay. What else we can have? U bar delta x of, let's write every term, then we will see. U bar delta U dash by delta x plus U dash delta U bar by delta x plus U dash delta U dash by delta x. These are the four terms. Similarly, V bar delta U bar by delta y plus V bar delta U dash by delta y plus V dash delta U bar by delta y and V dash delta V dash, sorry, U dash by delta y. Hectic in calculation part, but can be written. Okay, delta U bar by delta z plus W bar delta U dash by delta z plus W dash delta U bar by delta z plus W dash delta U dash by delta z. Perfect. This is the LHS. RHS, the RHS has minus 1 by rho bar plus rho dash delta P bar by delta x minus 1 by rho bar plus rho dash delta P dash by delta x plus F V bar plus F V dash. Perfect. This should be the thing. Okay. Now, what else we can do based on the perturbation method? Look at this. The third point. Product of a perturbation term is 0. Is there any? Yes. See this. U dash into delta U dash. It's a product of perturbation term. Put that 0. This. Can we put that 0? This one can be neglected. And hence we get a final thing, right? Okay. Now, next thing, what we can do is that let's see if we just use the second point, that both base state as well as perturbed state must follow the dynamic equation. Okay, so let's say that base state follows the equation. Okay, if base state follows the equation, then how it will look like? It will look like delta U bar by delta t plus U bar delta U bar by delta x plus V bar delta U bar by delta y plus W bar delta U bar by delta z is equal to minus 1 by rho bar delta P bar by delta x, okay, plus FV bar. Isn't it? Now this is already gone. It's not there because U bar is time average. This thing is still there. Okay. So can I put this? If this is true, can I come here and chop off those terms? See, U bar delta U delta x, then this, all the base terms. This rho bar, see, rho bar is much greater than rho dash. This is the first assumption. So this can be chopped out and FB bar can be chopped out. So what you get finally, okay, is this delta U dash by delta t. After all these assumptions, we are getting this U bar delta U dash by delta x plus U dash delta U bar by delta x plus V bar delta U dash by delta y plus V dash delta U bar by delta y plus similarly W bar dash by delta z plus W dash delta U bar by delta z, which is equal to minus 1 by rho bar plus rho dash delta P dash by delta x and plus FV dash. This is the equation which we are finally getting based on all the three assumptions. Okay, now we will give a final assumption that this is for our simplicity. This is the actual answer. Okay, that after Following all the three assumptions which we have taken for the perturbation method, we are getting this as the final result. Okay, but on top of this, if we put some final assumption, we can reduce the equation much more simply, or we can simplify the equation. What is that? That your base two, u bar, v bar, w bar, and whatever is there. Okay, fine. Up to this are uniform in space. Means they are constant. So they are not a function of x, y, z, which is a very dangerous approximation. You should not do that. But for simplicity, we can make it, at least for solving purpose. Okay. So if you do this, what you will get? Delta u dash by delta x plus u bar. So this term will go. Okay. Then this term will go because u bar by delta y is 0, and this term will go. Okay, so finally we will get delta u dash by delta x. Sorry. Okay, u bar delta u dash by delta x plus v bar delta v dash by delta y plus w bar delta u dash by, sorry, this is u, by delta z is equal to minus 1 by, you can make it rho bar because here again rho bar is much greater than rho dash, delta p dash by delta x plus f v dash. This is the final. After making this final assumption, we can simplify it to some perturbation terms. Okay. So this is the now the final equation. Now you can solve based on other equations also. You can solve the further for getting the solution of the u dash or whatever you have. Okay. We will apply this. Now we will apply this perturbation technique to derive other waves. Okay. Now, within this part, is there any question? If you have, you can ask. After that, then we can start. Okay. Just think in this, whatever we have done. Tell me. हाँ नहीं है, एकदम नहीं है, एकदम नहीं है, तो एकदम बोलूंगा कि गलत अप्रोक्सीमेशन है. कांस्टेंट हमेशा हर जगह नहीं रहता है ना, चेंज तो होता ही रहता है मीन मीन. तो रीजियनल, एक रीजियन में अगर हम लोग देखें, सपोज जो मॉनसून रीजियन है सपोज इंडिया का, वहां पे ऑलमोस्ट मैं बोलूंगा कि जो जोनल विंड स्पीड है ऑलमोस्ट सपोज कांस्टेंट है, सपोज एक छोटा सा रीजन, देन इट इज सो. बट ये नहीं है, ये सही नहीं है. हम लोग जब नेक्स्ट अब वेव्स वगैरह डिराइव करेंगे तब हम लोग अपने हिसाब से एजम्पशन लेंगे. तो हाँ हाँ, पर्टिकुलर रीजियन के लिए एग्जैक्टली. ठीक है. ओके, चलो नेक्स्ट we will go to acoustic waves. This we will apply this method now to some sound waves, then gravity waves, and other things. Okay, so we will derive certain things. Okay, and based on these waves, what we will discuss now, there will be some very simple numerical questions in the assignment 5. I've seen that. Okay, so first is the acoustic waves. First, I will give down some properties of acoustic waves, and then we will go to in deriving the solution of those waves. Okay. So first is acoustic waves means the sound waves. Okay, in atmosphere where these sound waves can come, uh, huge thunderstorms. When there is a thunderstorm forming, you see that you hear the loud sound along with the lightning. Okay, so those sound waves which travels, that can be related to these atmospheric acoustic waves. Okay, one of the examples. Fine. First point is that these are longitudinal waves. Okay. As a physics student, we all know what are longitudinal waves. That your particles will oscillate, will oscillate parallel to the direction of the waves. Right? This is the definition of longitudinal waves, direction of wave propagation. Okay. So suppose this is the one, so this is how the particle will oscillate and the wave will also travel in this direction. So that is what your uh, longitudinal waves are. Second is that sound or acoustic means sound. Study of sound is acoustics. Sound is propagated propagated by alternate adiabatic compression and expansion. This is also very much known that how the longitudinal waves generally travel. There is a compression and rarefaction, the way the sound waves generally travel. Okay, the compression and expansion of the medium. The medium will not change. It just will transfer the vibration uh, in the direction of the wave. So compression and expansion of the medium. This is how the sound waves will travel. Okay. So since it is a longitudinal wave, one of the things is that we will assume that transverse oscillations, transverse oscillations will be equal to zero. Okay. So now what we will do is that consider air parcels or parcel, let's say, move in x direction. This you can take in any direction. I am taking it in x direction. Okay. So if the air parcel is moving in x direction, then the wave is assumed or wave will travel. Wave travels in the same direction. Okay. Wave travels in the same direction. So if I am taking x as the direction where the air parcels are also moving and the wave is also propagating, then transverse oscillations will be zero. So V and W are kept zero. First point. Okay. And since we are again talking about the x direction motion, we will assume only the, or we will use only the zonal momentum equation. Zonal momentum equation. So what is the zonal momentum equation? Du dt plus 1 by rho delta p delta x is equal to 0. This is the first equation, which can be written as delta u delta t plus u delta x plus 1 by rho delta p delta x. Why other terms are 0? Because v is 0 and w is 0. Okay, so you can get this. Fine. And yes, that's all. Next, Coriolis term will also be 0 here because FV, if you remember, so that is also 0. One thing we will use, so one, we have used the zonal momentum equation because we have assumed that in the x direction the motion is happening. Second, conservation of mass, which will always be valid, right? Conservation of mass. So what does that say? Mass continuity equation, which is d rho dt plus rho delta u delta x. Other terms will be 0 because v and w are 0. So only this, correct? And another is that we will take the thermodynamic energy equation and we will take this version of the thermodynamic energy equation. We have derived it. d dt of log theta is equal to 0. Why? Because it's an adiabatic compression and expansion. So adiabatic process. So d dt of log theta, where theta is what? Potential temperature. Potential temperature. Okay. This is coming from the energy conservation, thermodynamic energy equation. Okay. And what is theta actually? P upon density gas constant, P naught by P upon R by Cp. Okay. But P naught is the reference, which is generally 1000 MB constant. Okay. Fine. So if this is your thing, then what we can write is that theta can be written as, uh, let's see, P naught to the power R by Cp divided by density R. Can I write P1 minus R by Cp? Yes, we can, because there is a P to the power R by Cp in the denominator and P is there in the numerator. So we can write this. Okay. So theta can be written as K constant times density P R by Cp minus 1. Why? Because I'm just keeping this in the denominator. So just uh, simply by taking a negative sign, we can write it. Okay. So finally we are getting this. Now, next what we will do is that take log of this. So log of theta is equal to log of k divided by rho p to the power r by cp minus 1. Alright, this is what you have. Now, see, r by cp minus 1. So, r minus cp divided by cp. What can be written as r can be written as this cp minus cv. You all know this. Minus cp divided by cp. Cp Cp cancels. What you get is minus Cv by Cp. And if you remember from our uh, 11th or 12th class chemistry or physics, we call this Cp by Cv ratio as gamma. And it changes for a diatomic gas, triatomic gas. So it is just called as gamma. Okay. Can I write therefore R by Cp minus 1 as minus 1 by gamma? We can. Okay. So finally, what we get is that log of theta is equal to log of some constant plus 1 by gamma log p minus log of rho. How? Just look at this expression. So log of k, okay, minus log of rho, which is there, and this is minus 1 by gamma. So it is already in the denominator, so it becomes plus. This will be the expression. Perfect. Now, let's take time derivative of this. So ddt of log of theta ddt of log of k plus 1 by gamma is a constant ddt of log of p minus ddt of log of rho. This is already from thermodynamic energy equation. It's an adiabatic process, 0. Okay. So 0, this is what? Constant 0. Time derivative of a constant is also 0. So what I get is 1 by gamma. Can I write this as dp dt minus? Can I write this as d rho dt? Perfect. We can do that. And by just writing it on the other side, we can write this. dp dt is equal to 1 by rho d rho dt. And 1 by rho d rho dt. Can I go to continuity equation? Yes. So 1 by rho, if rho is divided here, 1 by rho d rho dt will be minus delta u delta x. Okay. So 1 upon gamma p dp dt is equal to minus delta u delta x. From where? From mass conservation or from mass continuity. Okay. This step to this step to mass continuity. So finally the equation comes out to be 1 upon gamma p dp dt plus delta u delta x equals 0. So this is another equation we are getting. So based on mass conservation and energy conservation, we are getting this. Thermodynamic energy conservation, we are getting one equation. Second equation based on the motion of the air parcel, zonal momentum equation. So these are the two equations which we will consider. Try to create a wave equation. From there, we will try to assume a wave solution and try to find out what will be the possible solution. Okay. So this is my second equation. And earlier, this zonal momentum equation, this as my first equation. Okay. So as you can see, mass and mass conservation is there, momentum conservation is there, everything is there. Okay. Now we will try to derive using perturbation technique. Fine. Let us list down the equation again and then start deriving. So zonal momentum equation gives you what? Delta u delta t plus u delta u delta x plus 1 by rho delta p delta x. Put that equal to 0. This is the first equation. Okay, fine. Second equation is delta p delta t plus u delta p delta x. Okay, this one. dp dt we are opening, but v and w is 0, so I am not writing that. Plus gamma p times delta u delta x equals 0. So these are the two equations. Now we will apply the perturbation method. Okay, so we can write, since u is now a function of x and t, because in y and z there is nothing. So u of xt is u bar. Okay, that is, it is for a very short region. We have assumed that u bar is constant. Okay, plus u dash x comma t. Similarly, vx comma t, p bar plus v dash x comma t. What other terms are there? Rho is there, is equal to rho bar plus rho dash x comma t. And finally, P, the pressure, is 40 P bar plus P dash x comma t. Okay, so everywhere it is mentioned that your base state is almost a constant state. That is, there is a zonally average state and the time mean state. Okay, so it is not varying with space and time for the time. Okay, now we will apply these things. Perturbation method, you know, these things will be applied to these and this equation. So let's do the first equation. Delta delta t of u bar plus u dash plus u bar plus u dash delta delta x of u bar plus u dash plus 1 by rho bar plus rho dash delta delta x of p bar plus p dash, which is equal to 0. This gives you delta u dash by delta t, because u bar is invariant with time, u bar is invariant with space. Keep it like this, and you get delta u dash by delta x plus 1 by rho bar delta p dash by delta x equal to 0. So here I have done two steps. Let me tell you. Okay, let me just derive it once and then you will understand. It's simple thing. Okay, let me write all the terms. Okay, okay. So delta u dash by delta t plus u bar delta delta x of u bar plus u bar delta u dash by delta x plus u dash delta u bar by delta x plus u dash delta u dash by delta x. I will recommend you whenever you do these kinds of calculations, write all the terms and then apply the perturbation technique. Okay, fine. Are we missing something? No, these are the points. Okay, rho bar is larger than rho dash. Keep it like this, and 1 by rho bar delta p dash by delta. Okay, this is the assumption that rho bar is much greater than rho dash. Put that equal to 0. U bar is not varying with time, so this is 0. Anything else? Delta U bar delta X will also go to 0. Okay. Further. Yeah. This will also go to 0 because P bar is invariant with X. We have assumed. Done. Nothing else. And also, if you don't want to ignore that, you can see that this is the base state. Okay. This is the base state. This is also the base state. So this will automatically get cancelled. Fine. So finally, we are getting delta U dash delta T. This, this term product of perturbation. This will be 0 and this term. So delta U dash by delta T plus U bar delta U dash by delta X. Okay, plus 1 by rho bar delta T dash by delta X equal to 0. So next time, from the next time onwards, I will not write all the terms, just write the actual perturbation equation. Whenever you derive, you write all the equations, apply perturbation method, and see whether you are getting this expression or not later. Okay. Similarly, if you apply perturbation method to this equation, which we have derived from the continuity and thermodynamic energy equation, you will get this delta P dash by delta T plus U bar delta P dash by delta X plus gamma P bar delta U dash by delta X equal to 0. Okay. So these are the final perturbed equations which we are getting. Now look at this. Now what we will do is that see this. The first equation, can we write this del T of plus U del X, this times U dash plus 1 by rho bar delta P dash by delta X equal to 0. Can we write like this? Yes, because it is operated on this. Similarly, second equation del T plus U bar del X of P dash plus gamma P bar delta U dash by delta X. Yes, we can write this. What I will do next is that we have to create a wave equation. Wave equation means one time part will be there and one space part will be there, like this. Okay, general wave equation which we use in physics. Okay, so what I do is that in order to do that, we will let us operate. Let us operate del T plus U bar del X, this on equation 2. So this is 1, suppose this is 2. So on 2. Let us apply this. So what will happen? If I operate this, we get del T plus U bar del X square P dash plus gamma P bar, all are some kind of a constant. Del X you can keep in this. Can I write this? U bar del X? We can, into U dash, that is equal to 0. So finally we are getting something like this. Okay. Now look at this. Let me write it again so you will understand. U bar del X of square P dash plus gamma P bar del X of del T plus U bar del X of U dash, which is equal to 0. Look at this term, del T U bar del X of U dash. See this. So what is that? Negative of this term. So just put that in this equation. So the same will be here, del T U bar del X whole square P dash plus gamma p bar del del x of minus 1 by rho bar delta p dash by delta x. Correct? This is equal to 0. Perfect. So again, I have to write u bar del del x whole square of p dash minus can be taken. Minus can be taken here. Minus gamma p bar. Rho bar can be taken outside. It's a constant. Del square p dash by del x square. See, it came out to be a wave equation kind of a thing. Okay. Now, what can be written for this? This is actually can be written as delta square by delta t square. Simple mathematics. A square plus 2ab and plus b square. Okay, times p dash plus or minus gamma p bar by rho bar delta square p dash by delta x2 equal to. Now we have got a wave equation. So this is my wave equation. Now I will what the major step here is that you assume a solution to the wave equation. So let us, since we have an equation with p dash, let us assume p dash is equal to a e to the power iota kx minus omega t. This is the general solution of the wave equation. So how to solve now? Put this p dash on this on the wave equation. So put p dash on wave equation and you will get to know what the things will be. So if you put this solution on the wave equation, you will get a dispersion relationship. That is, you get a relation between this omega and k. And that will help you to understand the wave speed, whether the group speed exists or not, okay, and many other things. And mostly these unknowns, k and omega, will fulfill this equation. Okay, let's see. So put that in the main equation. Okay, so del 2 del t2 or del square by del t square p dash will be what? P dash is this. So if you do time derivative, what it will be? Minus iota omega will be squared twice and a e to the power iota kx minus omega t as it is. Okay, so can we write this as minus square will be gone minus omega square p dash, right? Similarly, 2 u bar delta delta x delta delta t of p dash. So what it will be? 2 u bar del del x will give you iota k, del del t will give you minus iota omega times p dash, and finally del square by del x square u bar square p dash. What it will give you? U bar square and iota k whole square p dash. So this gives you the first term. And the last is minus gamma p bar by rho bar delta square p dash by delta x square, which is nothing but minus gamma p bar by rho bar iota k whole square p dash. That's all. So now if you write all these terms, what you get is this. So minus omega square p dash minus or plus 2 u bar omega k p dash minus u bar square k square p dash, alright, and you get the plus gamma p bar by rho bar k square p dash, that is equal to 0. Alright, this is what you get. P dash from all the terms you can cancel. You can cancel the minus even. So divide by minus p dash. If you do that, you get what? Omega square plus. Okay, you have minus. So 2 u bar omega k plus u bar square a square minus gamma p bar by rho bar k square. Put that equal to 0. Finally, can I write this entire term as omega minus q bar k whole square? Yes, we can. Minus gamma p bar by rho bar k square equals 0. And finally, omega minus u bar k whole square, which is equal to gamma p bar by rho bar k square. Take the square root. Omega minus u bar k gives you plus minus root over gamma p bar by rho bar into k. So finally, what you are getting, omega is equal to u bar plus minus root over gamma p bar by rho bar into this whole times. Okay. So this is what you have. This is the dispersion relation. Okay, this is the dispersion relation. A relation between omega and t. Question is this wave a dispersive wave or not? So how to check that? See the phase speed. How to check the phase speed? Very simple. We have derived what is the phase speed. C is omega by k. Just do that. So C, which is nothing but omega by k, will be u bar plus minus root over gamma p bar by rho bar. Is C a function of k? No. C is not a function of k. It's not a function of the wave propagation. So it is a non-dispersive wave. I have told you that I will show that which waves are non-dispersive, which waves are dispersive. And in the non-dispersive wave, we have given this example of acoustic waves. So you can see here clearly that it is not a dispersive wave. Okay, so non-dispersive. Fine. Let us further see. So C is equal to U bar plus minus root over see gamma. Okay, P bar. P bar from ideal gas law can be written as rho bar R into T bar. P is equal to rho R T, ideal gas law in thermodynamics. So if you just put that rho bar R T bar divided by rho bar, rho can be cancelled. So what you get? C is equal to U bar plus minus root over gamma R T bar. And if you put several values here, you will get it nearly equal to some 340, something like this, right? The speed of sound. Okay, so this is the speed of the sound, and yeah. So now, if say suppose u bar, the base wind or the mean wind, if it is greater than zero, say eastward, right? If the mean wind is eastward, then what will happen? So this is the direction of the winds, okay? And here, from where the sound has started, okay? So you will see that your omega, your frequency, will be higher, will be higher in the eastward direction because this is positive, okay? Whereas here you will get omega lower, okay? So, so this is the westward direction. Okay. So suppose this is your source, and if you are standing here, you will get more of the sound waves, whereas on the opposite side, if you stand, you will get lesser. the sound frequency, you will get less. Okay, so these are couple of things. Okay, so base winds, in that way, the base winds may matter. But sometimes what happens is that you can keep your U bar zero. If there is no zonal velocity, then how it will work? So only with the perturbation, whether the sound waves will be generated, it can, but you will only get this sound waves, right? So these are the couple of things which I wanted to show. That is why it is called a means we have told multiple times that it is a non-dispersive wave. We have proved that it is a non-dispersive wave. Okay, and yeah, one of the examples of these acoustic waves, as I have already told, the thunderstorm, the thunder generation. Okay, that when it travels is what uh, is your this waves. Okay, and you can see that speed of the waves depends on this average temperature also. Okay, and when there is a tremendous thunderstorm, the temperature goes huge. Okay, and in that way, that's why the sound is something what which we heard, which is very strong. Okay, so that is also another important part for the acoustic. The next thing after the acoustic wave is the second wave, which is the shallow water gravity wave. We will look into this shallow water gravity. And I will just quickly give you a hint of the deep water gravity wave and its group velocity and phase velocity. I will not, there is no derivation properly, but for shallow water, we have a derivation. We will do that. And then I will just give you a hint because there is, I think, in the assignment 5, there is a question on some storm related thing. Okay. So when you have over a ocean, suppose you have a storm which is generated, it will try to create waves. If you remember, whenever you have cyclones, large tropical cyclones, these are also tropical storms, right? So it has been, it is generally advised to the fishermen near the coastal area not to go for fishing during this day to that day because the storm is coming and there will be huge wave surges. That means the wave height increases because of the storm formation. So why it happens? Because it gives the energy, the storm's energy is being conveyed into the water waves. Okay, and the energy is transferred based on that. So, in what it does is that when a storm is formed, it creates these deep water gravity waves, and on creation of deep water gravity waves, it tends to generate some group velocity because, as you know from the physics also, group velocity generally carry the energy of the waves. Okay, so that is the point in the assignment 5. Some question is there. I don't remember which question. So there, that the group velocity related expression you need to solve the question. Okay. So I will just at the end of this particular session, I will just give you the expression of the group velocity for the deep water waves, and I have already given you the concept of what is happening when a storm is formed over the ocean. Okay, so then you can apply and try to see. We will see in the next problem solving session. Okay, but right now, let us follow the shallow water gravity wave. This is another wave, and interestingly, you will see that this is also a non-dispersive wave. All those dispersive wave derivation, we will do it in the next problem solving session, which is the internal gravity waves that we will see. Okay, currently we will do shallow water gravity, and you will find some good numerical question from this. Very simple also, but yeah. Okay, so shallow water gravity wave. Again, some properties. Generally, you have a fluid, whether it is ocean or atmosphere, has internal discontinuity. In what? Discontinuity in density, temperature also. Okay. In ocean also, if you look at upper layer having higher temperature, some particular density. As you go down, density might increase, density might decrease from different layers. So there is some density discontinuity. Okay. Based on this density discontinuity, you get to generate these waves. Okay. So restoring force in case of gravity waves, as the name suggests, is the gravity. Restoring force, which is gravity, is in vertical direction. So, unlike the previous one, acoustic waves, this is transverse waves. Okay, this is transverse waves. Why? Because it is something like this. Particles motion is like this, and the wave is propagating like this. Okay, so this is uh, the transverse waves, but acoustic waves are longitudinal waves. Okay, this is one of the difference. Okay, and where the waves will propagate? The waves propagate along the interface between two layers. So wherever there is a discontinuity, there in that discontinuous interface, the waves will tend to propagate. Okay, so I will make a simple figure to make everything understand like this. And you have a base here. At any from the base, any point of the wave has height h. Okay, and let us consider that this is your base mean state, I would say. Okay, this is your mean state. All right, and this is some high region. This is some low region, as you can see. This has some density rho 2. This has some density rho 1, and this is your z direction, and this is your, let's say, x direction. You can take y also, doesn't matter. All right, and here another thing is that we are not considering effect of rotation. No rotation. Or what I mean is that no Coriolis effect. Just I'm ignoring that for the time being. Okay, which is one of the things. Okay, so delta theta z, that is in the z direction, delta p delta x, if you do this mathematically, just if you do, can I write del x of delta p delta z? Yes. And what is delta p delta z? Using hydrostatic approximation, you can write it as rho times g, which is constant, which is becoming zero. That means no variation of density in x direction. Why? From this expression. Because g is already a constant. So delta rho delta x is zero. Density is not varying in x direction, which is true. I have kept it like that. Only in the z direction it will vary, but the pressure gradient, okay, delta p delta x, it does not vary with z. So see here I have applied hydrostatic approximation. Okay, hydrostatic approximation. This is generally applied where your height scale is much less than the length scale. Okay, then only this hydrostatic approximation will be applied. So this is one of the things. Okay, these are the couple of basic things which you require. Okay, now let us make some diagram here. Okay, let's say this is your A point, this is your some B point, this is the highest point here. Okay, and you know that horizontally, this is also getting some atmospheric pressure or some pressure P. This is also getting some pressure P, this point in the same line. But the pressure at A will be different, pressure at B will be different. Why? Because the medium here. Here it has density rho 2, whereas here it has density rho 1. Okay, so let us look at that. So at B point, P plus say, delta P1 will be the pressure, which is P plus rho 1 G delta H delta X into delta X, whereas A it is P plus delta P2, which is P plus rho 2G delta H delta X into delta X. See, this is your B point. That's why rho 2 comes. I'm sorry, something. Yeah, this is your A point. That's why rho 2 comes here. Okay. In at B, it is the rho 1. See, this one. And delta H is H is the total height. Let us say the base height is capital H and the perturbations is small h. Okay. So this h is equal to capital H plus some h dash we can write. But yeah, so the h variation is taking place. You can see here at A, the h is up to this. At B, the h is same, but based on this. Okay. What I am trying to make is that this h is from the base to the wave surface. So wave surface at A is here, at B is here. So that's why the delta H delta X variation is coming. Okay. Now, now what is delta P delta X? That is nothing but P at your B minus P of A, right? P of this is B, right? So X is in the positive direction from A to B. So P of B minus P of A. That is what I will do. So P plus delta P1 minus P plus delta P2 divided by delta X. Alright. So what you get? All things will be cancelled. You get rho 1 minus rho 2. You get delta H delta X times delta X divided by delta X. This goes. Finally, you get G rho 1 minus rho 2 delta H delta X. What about the pressure gradient? 1 by rho delta P delta X is G rho 1 minus rho 2. I will take the density which is at the lower end. Okay. So it will be some rho 1 delta P delta X. Alright, this is what you get. Now, since it is a transverse wave, we are taking XZ momentum equation. XZ momentum equation. Okay, you cannot neglect the Z part. So what you get? Delta U delta T, U delta U delta X, W delta U delta Y, sorry, delta Z is equal to the pressure gradient force. So G, can you write it delta rho divided by rho 1 delta H delta X. So it will be H. Okay, this is your first equation. Let's see the mass conservation or continuity equation. What will it give? It will give delta U delta X plus delta W delta Z is equal to 0. Okay, so this is what you will get. Also, U is assumed not to be a function of z. Why? Because see, u depends on delta p delta x. And we have already proved that delta p delta x is not varying with z. So u is not a function of z. Therefore, delta w delta z can be written as minus delta u delta x. Okay, this is one of the part. And so if I have this, then what will happen? I can integrate this like this way because u is not a function of z. So I can do it like this. So w at h is equal to 0, w at some height h, 0 to h. So w at h minus w at 0 is equal to minus delta u delta x. There's nothing to do with z, can come out into h. Okay. And at the surface, the vertical velocity is 0. So only we have w of h, which is minus delta u delta x into h. What is w of h? Can I write it dh dt? Right? So this h, which I have already assumed that from the base to the surface, at every location x, it is varying with height. Right? So that is what is wh. H times delta u delta x with a negative sign. This is another equation, which is the continuity equation, which can be further written as in terms of partial derivatives u delta h delta x is minus h delta u delta x. Okay, that's all. Okay, why are we not writing w delta h delta z? Because h does not vary with z at one point. If you fix your x, suppose this is the point. Is it varying with z? No, it is fixed h. But if you go from one point to another, allow the x to vary. This then h can change. Okay, so that's why h delta h delta z is 0. So that's why only this will come. So what we will have is that two equations. One is you have delta u delta t plus u delta u delta x plus your what you have is u is not a function of z. So w delta u delta z we will skip. This will be 0 because u is not a function of z is equal to what you have here. So you can keep it like g delta rho by rho 1 delta h delta x equals 3. This is the first equation. Second equation is delta h delta t u delta h delta x plus h delta u delta x is equal to 0. So these are the two equations. Now you apply the perturbation method. So u is equal to again u bar plus u dash. H is equal to, you can keep it like this, h dash. Okay. And assuming that these are constant. Okay. Now if you apply the perturbation method, I am not deriving everything. Just like the previous acoustic waves, same way. I'm just writing the expression delta u dash delta t plus u bar delta u dash delta x plus g delta rho by rho 1 delta h dash by delta x equals 0 and delta h dash by delta t plus u bar delta h dash by delta x plus h delta u dash by delta x equal to 0. So these are the two perturbation based equations. Fine. Now what we will do is that one thing you can do is again we can write this equation like this delta delta t plus u bar delta delta x of u dash is equal to minus g delta rho by rho 1 delta h dash delta x. Okay. And here in this, we will operate with this delta delta t plus u bar delta delta. Okay. So what I will get from the second equation on 2. Okay, this is the second equation. This is the first equation. So if you operate this, what you get? Del del t plus u bar del del x whole square h dash plus h del del x and the same del del t plus u bar del del x times u dash, that is equal to 0. So del del t plus u bar del del x whole square h dash plus h. Now, what is this del del x of, sorry, this thing? This thing is already here. So just put that. So del del x of minus g delta rho by rho 1 delta h dash delta x. That's all. Put that equal to 0. Finally, del del t plus u bar del del x whole square h dash minus gh by rho 1. Keep the delta rho also outside. Delta square h dash by delta x square. Put that equal to 0. Why we can do that? Because rho is not varying with x. We have shown that already. Okay. So this is my, what you call as the final wave equation. Okay. It is in h dash. The best way to solve is that assume a solution. H dash is equal to a e to the power iota kx minus omega. And if you do it, I have already shown it for the acoustic waves. I will now write directly. Okay. So, or yeah. Okay. So this will be del del t whole square, that is minus iota omega square h dash. Okay. Plus 2 u bar. Okay. Del del x and del del t. So it will be minus iota omega and iota k h dash plus u bar square del del square x. So it will be iota k whole square h dash. So the first term is done. Second term is minus gh delta rho by rho 1 this delta square. So what is that? Iota k whole square into h dash. That is equal to 0. Let us solve it. Minus square is 1. Iota square is minus omega square h dash. What is coming here? So iota square is minus 1. Minus minus becomes plus. It will be 2 u bar omega k h dash. Iota square minus u bar square k square h dash minus gh delta rho by rho 1 iota square minus. So it will be plus k square h dash. Put that equal to 0. So divide by minus h dash. If you do that, you get omega square minus 2 u bar omega k plus u bar square k square minus gh delta rho by rho 1 k square is equal to, again, then we write this as u bar into k whole square minus gh delta rho by rho 1 k square equal to 0. Finally, omega minus u bar k whole square is equal to gh delta rho by rho 1 k square. Take the square root u bar k plus minus root over GH delta rho by rho 1 into T. So omega is U bar plus minus root over GH delta rho by rho 1 times K. Okay, so this will come out to be the again dispersion relation for surface gravity waves. Okay, now we will take last assumption that your rho 2 is much smaller than rho 1. Just like uh, the rho 2 is air and your rho 1 is, let's say, water. Okay, so rho 2, which is air, is having much lower density, like 1.28 kg per meter cube, whereas water is about 1000, right? So, if this kind of approximation is valid, rho 2 is much less than rho 1, then delta rho, okay, delta rho can be assumed to be equal to rho 1 because it is nothing but rho 1 minus rho 2. So, can we then write like this? Omega is equal to u bar plus minus root over gh rho 1 by rho 1 because rho 1 is the largest. So this cancels. And so finally, this is my dispersion relationship based on the assumption which I have told. So root gh. What is h? H is the depth of the fluid or depth of rho 1 density fluid, which in case you can say water or whatever you want. Okay, so it's the depth of the fluid. Fine. And again, so this is what is your dispersion relation. Okay. Can we say that it is a dispersive wave or a non-dispersive wave? For that, check the phase speed. So how to see the phase speed of a wave? Just take omega by k, that is equal to nothing but u bar plus minus root g. So you can see that c, the phase speed, is not a function of the propagation vector k or the wave number. So if c is not a function of wave number, we can clearly see that this is non-dispersive. Okay, so this is also a non-dispersive wave, just like the acoustic waves. Acoustic waves, which we have derived, is the another. So this is the common thing between acoustic waves and a surface water gravity wave. But acoustic waves are longitudinal wave; these are transverse waves. So this is one of the things to know. And generally, one problem will be that the depth of ocean, average depth. Okay, so if your average depth of ocean is roughly about 4 kilometers. Okay, so what will be the speed of the gravity wave? Can we calculate the speed of the gravity? This is a question you can do. Okay, I think there might be a question in the assignment also. You can try that. We will discuss, of course, the assignment in the next problem solving session. Okay, so this C will be equal to root GH. Don't worry about U bar. Okay, whenever you have been asked to calculate the phase speed of the gravity waves or phase speed of any wave, just assume this U bar to be zero for the time being because the phase speed is actually coming from this. Okay, so just take root GH and try to calculate. So G is 9.81 meters per second square. H is 4 kilometers. So it's about 4,000 meters. You can keep this as 10 for simplicity. So what you get? 2 into 10 to the power 2, right? Meter per second. So it will be 200 meter per second. So in general, if you have an ocean whose average depth is 4 kilometers, the surface gravity waves will uh, have the phase velocity 200 meter per second. Average means, but in general, it might not happen. It may shift. There are many locations where uh, the depth is not 4 kilometer. Somewhere it is 5, somewhere it is 3, somewhere it is 11 kilometers, like in the Mariana Trench. Okay, so there things will change, but that happens locally. So that's all. I think also one of the important thing is that for the surface gravity waves, things. Ah, yes, yes, right. बिल्कुल डेंसिटी के ऊपर डिपेंड करेगा, बट मैंने यहाँ पे क्या किया, मैंने बोला कि एवरेज डेप्थ ऑफ द ओशन, इफ यू टेक द इंटायर ग्लोब समवेयर, मैं वही बोल रहा था कि कहीं 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 पे 11 किलोमीटर का डेप्थ है, कहीं कहीं पे 4 किलोमीटर का डेप्थ है, कहीं कहीं पे 3 किलोमीटर का डेप्थ है, बट मैं क्या करूँ कि एवरेज डेप्थ, इन सब का एवरेज ले लें, तो एवरेज डेप्थ ऑफ ओशन जो है दैट इज 4 किलोमीटर, 4 किलोमीटर है, ठीक है। वो एवरेज डेप्थ अगर हम लोग कंसीडर करेंगे, फिर जो सरफेस वेव उससे जनरेट, हाइपोथेटिकल सिचुएशन है, समझ रहे हो, इससे हाइपोथेटिकल सिचुएशन, बिकॉज एवरेज एवरेज डेप्थ हर जगह तो नहीं होगा, मैक्सिमम जगह पे होगा, बट और जगह पे नहीं भी हो सकता है, वहां पे चेंज हो जाएगा, तो वो रीजन वाइज डिपेंड करेगा। बट मैं एक सिचुएशन एज्यूम कर रहा हूँ कि हर जगह सेम, एक ऐसा प्लैनेट है जहाँ पे 4 किलोमीटर ही है डेप्थ ओशन का, तो उसमें क्या हो, तो ये निकल के है कि उसमें, हाँ, हम्म, हम्म, हाँ, हाँ, नहीं देखो, इक्वेटर में जनरली ट्रेड विंड्स होती है ना, कि ऐसे विंड्स ट्रेवल करती है, तो इसके वजह से क्या होगा, वाटर वॉल्यूम जो है वो ऑपोजिट साइड में, एक मैन कुछ होता है, एक मैन पंपिंग टाइप का होता है, तो उससे वाटर डिस्प्लेस हो जाएगा, तो इससे क्या होगा, अपवेलिंग होगा यहाँ पे, कूलर रीजियन बनेगा, तो कूलर रीजन की वजह से यहाँ पे डेंसिटी बढ़ सकता है, ठीक है। तो हाँ, ऐसे ये तो सरफेस डेंसिटी हुआ ना, बट हम लोग क्या कर रहे थे, अब ये जो ग्रेविटी वेव्स में बता रहा हूँ, ठीक है, हाँ, ये हो सकता है सरफेस में कुछ है, एयर का डेंसिटी कुछ है, तो यहाँ पे वेव उस हिसाब से बनेगा, उस हिसाब से बनेगा, तो ट्रॉपिक्स में कुछ बनेगा, ट्रॉपिक ऑफ कैप्रिकॉर्न में कुछ बनेगा, जो तुम्हारा क्वेश्चन था, इक्वेटर में कुछ अलग तरीके से बनेगा, तो वो डिपेंड करेगा डेंसिटी ग्रेडियंट से। हम्म, सो सब कुछ डिपेंड करेगा, मैं यहाँ पे जस्ट एक सिंपल हाइपोथेटिकल केस ले रहा हूँ, सिमिलरली जो असाइनमेंट में क्वेश्चन मिलेगा उसमें भी वैसे ही होगा, ठीक है, वो डिपेंड करेगा, वो एब्सोल्युटली राइट। हाँ, 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 वही, राइट, राइट, नहीं नहीं, हाँ, ठीक है, ठीक है, उतना मतलब डेप्थ में नहीं जाना कि टॉपिक ऑफ, अगर उतना डेप्थ में वो लोग पूछ रहे हैं तो उन लोगों को वैल्यूज भी देना चाहिए, क्योंकि हम लोगों को इतना थोड़ी ना आइडिया होगा कि ट्रॉपिक ऑफ कैंसर में क्या आएगा, वैल्यू डेंसिटी का चेंज हो सकता है ना, डिपेंड करता है बहुत कुछ, और ऐसा कोई इक्वेशन भी नहीं है जिससे हम लोग निकाल सके कि इक्वेटर का डेंसिटी अगर ये है, तो ट्रॉपिक ऑफ कैंसर में जितना नॉर्थवर्ड जाऊंगा या साउथवर्ड जाऊंगा तो क्या डेंसिटी होगा, ऐसा कोई इक्वेशन भी नहीं है हमारे पास, तो है ना? हम्म। तो उतना नहीं सोचना, जस्ट अप्लाई, यहाँ पे जस्ट एप्लीकेशन के लिए, जस्ट सिंपल एक प्रॉब्लम के लिए। जब डीप जाओगे तो चीजों को और जानना पड़ेगा कि क्या है वहां पे, डेंसिटी क्या, ग्रेडियंट क्या है, ये सब। ठीक है, चलिए। तो thing is that for the surface gravity wave, one condition is this lambda is much greater than h. Lambda is the wavelength and h is the height, which we have already shown that h is much less than the length. That's why the hydrostatic approximation is valid. That's why the entire derivation is done. Another thing is that the deep water gravity wave. Okay, deep water gravity wave. Just I will give a simple expression. I will not discuss in detail much. So what was discussing is that if you have ocean and if you have some storm formation over the ocean, what will happen is it will create some waves undulation, which will go deeper. It will attenuate. The more it will go to the depth, the energy will attenuate. The amplitudes will get attenuate. Okay, but finally, in case of deep water gravity waves, you find that it is dispersive. Okay, it is dispersive. Hence, it will have group velocity, and we know that group velocity carries energy. Okay, it will carry energy. Now, what is the group velocity? So, in this case, your lambda for the deep water gravity wave, the lambda is like this. Oh, sorry, this. Okay, so lambda is much less than h, opposite to the condition of the surface gravity wave. Okay, here the wavelength is less than, much less than the depth of the fluid. Okay, in this case, your dispersion relationship becomes this, root over g times k. Now, if you do delta omega delta k, you will get some expression, right? So you can try that, delta omega delta k, or omega square is equal to gk, you write. So 2 omega delta k is g. So delta omega delta k is equal to g by 2 omega. Okay, so whenever you have some questions related to the storm over the formation over the ocean and to calculate how much time it takes for the waves to reach the coast, you can use this concept. Okay, and I can see it in assignment. Just try to use this concept of the group velocity and calculate the time it reaches for the waves to reach to the coast. Okay, so that's all. What else? That's all. This is the concept I wanted to give you for the assignment. Assignment 5. Okay. Uh, this might be useful for anything like storm formation, how much time it will take. And finally, also you have this formula is also important for the assignment 5. Okay. Other things are very general. So I don't think if you have understood these derivations and all, you will be able to get it. Very simple questions are there. So that's all. So we have discussed assignment 4 today, then perturbation technique, where these three are the important points for applying a perturbation technique. We have applied it, and we have tried to see the acoustic waves, its derivation. We have derived its dispersion relationship and proved that it is a non-dispersive wave. Then went to shallow water gravity waves, where also we have proved that is also a non-dispersive wave. And finally, I've given an expression of the deep water gravity waves, where uh, that which is dispersive in nature and that has a group velocity which carries energy. So any storm formation over the ocean has to go with the deep water gravity waves, and so you can apply that in the assignment questions. Okay. I stop it here. Now, if any question is there, you can discuss, or you apply these concepts. We will discuss the assignment file in the next problem solving session. Okay? That's it. Okay. Thank you. Okay. If you have no more questions, then let me stop them.